All right. So today, this is an informal talk by Erin Kado-Fong, who is a graduate student with Jenny Green at Princeton. She's going to tell us about dwarf galaxies and their structure.
Top back of lights.
Lights off. You know, there's plenty of light coming in through your office. We can turn all the lights off.
Yeah, keep your mask on.
Perfect, yeah.
Okay.
Even the upgoing lights, I argue to turn off.
Okay.
Try it. There's so much light coming in. You like it? Which way you like it?
This is fine, yeah.
All right.
Okay, great. So thanks so much for having me. Today, I'm going to be talking about structure, feedback, and formation, and specifically about dwarf galaxies in the wide field era. And of course, I have a lot of great collaborators that I've been working on this with. Jenny, who you heard earlier this semester, is one of them, but there's a ton of others. And in fact, there's so many that I'm going to have to show you a second collaborator screen later on. But my screen is frozen. Oh, there we go. Okay. So before I get into that, I really want to answer two questions. First, why study dwarf galaxies? And then second, why now? And before I answer those two questions, I do really need to answer an even more preliminary definitional question, which is, what do I mean by dwarf galaxy? And when I say dwarfs, which is not completely trivial, even for people who think about dwarf galaxies a lot. When I say dwarf galaxies, I really mean bright dwarfs. So I'm not going to be talking about the ultra faint dwarf galaxies today, but really more of these bright dwarfs with stellar masses in the range of about 10 to the 7 to 10 to the 10 solar masses, and halo masses of around maybe a few times 10 to the 10 to a few times 10 to the 11. And this is really driven by the goal of having a large sample at a few hundred megaparsecs, really going back to this idea that I mentioned in my title of looking at dwarfs in a wide field view. Okay, so what do I mean by dwarf galaxy? These bright dwarfs. So now we can ask, why study dwarf galaxies?
Progress.
And why now? So if you'll allow me one corny analogy, which if you've heard this talk before, will you allow me two corny analogies? We can kind of think of physics as these two dual ladders of theory and observation. And of course, both of these ladders support each other. We can make predictions from our knowledge of theoretical physics, which supports our observations. And then those same observations can go back and constrain what we know about physics from a theoretical perspective. And then if I extend this analogy a little bit further, I can think of each rung of the ladder as perhaps a different scale of physics that are all interconnected. So if I start at the largest scales, think about large scale structure, going down to galaxy properties, down to galactic structure, and then all the way down to star formation. And clearly this isn't a all-encompassing view of physics at different scales, but rather a largely self-serving sampling that connects to what I'll be talking about today.
I'm realizing that my career is right where those ladders meet. It feels like a very unstable spot.
Somehow it's an alarming picture. It evokes all sorts of imaginations of what can go wrong.
Maybe I'll add some supports into the picture for visual security. Right, but dwarfs sit at a very useful place in this ladder because their properties and their structures, due to their low shallow potential wells, are particularly sensitive to effects both from the environment, so at larger scales, and from things like star formation feedback at smaller scales. So we can really use dwarfs to interrogate our understanding of these various scales of astrophysics. And however, the problem, of course, is that dwarfs are low mass and therefore faint. And so basic questions about their population remains. So why study dwarf galaxies? Well, they're an important rung in our overall picture of the universe. And then finally, why now?
Can I ask?
Yeah.
So I used to include in my thoughts about that argument that AGN were unlikely to be important for the dwarf galaxies. Is that still is that still a thing I should think?
Well, I think it does look like the AGN fraction is dropping for lower masses, but that's really confounded with the difficulties in finding AGN in dwarfs. So I think that's still somewhat of an open question.
Okay,
I don't think they're totally irrelevant, but I don't think that, they dominate feedback in the way that they do for more massive galaxies.
Right.
Okay. So then we can think about why now. And really, when we think about modern surveys, we can say that they unlock these large scale dwarf studies. Clearly, this is a cutout of a more massive galaxy, but here I'm showing cutouts for one kind of typical spiral galaxy from DSS, so the mid-90s, SDSS, so late 90s, early 2000s, and then HSC, which is ongoing on the right. And you can see that for this more massive galaxy, even back in the 90s, we could say quite detailed things about the galaxy's structure on an individual level. Not to say that we're not learning a lot of new things about the structure of more massive galaxies as we go to more modern imaging, but just to say that even a few decades ago, we could say something quantitative and specific about their structure.
Are the little points of light in the background, those are just background things, they're not dwarfs, is that right?
So
On the right, where with the higher
These?
resolution. Yeah, for example.
yeah, these
It's not
background
associated with the dwarf
galaxies.
galaxy.
No, they're not associated. Yeah, I think this is a high redshift spiral. These are too, and then these are the point sources are even higher redshift.
It does look like there's diffuse blue light though, right, associated with dwarf when you see it in.
Yeah, I think
Yeah.
that there's, especially you can see it in HSC and SDSS that these are definitely getting farther into the outskirts of the galaxy.
It to me it almost looks like there's some kind of tidal blue feature on the lower left coming off, but it might just be.
I think this might be an Imogen artifact.
I see.
Yeah. So, but if we go to dwarf galaxies now, you can see that the picture changes pretty dramatically. So back in the 90s, the detection is extremely marginal. You really only know that there's a detection because you can see it in the other two cutouts. And then in SDSS, you're starting to get at the main body of the galaxy. You can maybe see the brightest star forming region, but it's only with modern imaging that you can really start to say something specific about the structure and composition of these dwarf galaxies on an individual level in wide field surveys. So I talked quite a bit about HSC for a purpose. Most of the imaging that I'll be talking about today does come from this Hyper Supreme Cam Subaru Strategic Program, or HSC SSP. Just to give you some fast facts, if you're not familiar, this survey covers about 1,000 square degrees on the 8-meter Subaru telescope in Hawaii. It has a 90 arc minute field of view. The reduction is built on the same science pipeline that LSST will use. And it's kind of the classical 3-tiered wedding cake structure of the wide layer, deep, which spans a few tens of degrees, and then the ultra deep, which is a few degrees. We just had our third public data release, which is 600 square degrees at nominal survey depth. And I just want to point out to anybody who's interested in getting ready for Rubin and LSST, that as I mentioned, this is built on a very similar science pipeline. And the deep layer is at nominal LSST tenure depth, pretty close to it. Okay.
can you just remind us where that is where that 600 degrees is on the sky? That's something I should know.
So they're all pretty equatorial, and then
Okay.
there's a more northern.
Okay.
I'm not entirely sure where the 600 is out of the full 1,000.
All right,
I think
yeah.
it's mostly equatorial.
Okay.
Okay. So to go a little bit deeper in on the relationship between HSC and statistical dwarf studies, HSC is really well poised for wide field dwarf studies because of its depth, its breadth, and its resolution. So as I mentioned before, the wide layer covers about 1,000 square degrees in GRIZY, and the surface brightness limit is at about 28.5 magnitudes per square arc second in the I band, with an average C of 0.66 arc seconds. So quite high resolution. And HSC really provides this deep and high resolution view of the low surface brightness universe. And to give you a few examples, this can be things like individual stellar halos out to 100 kiloparsecs, clearly more massive galaxies. We're not measuring dwarf galaxy stellar halos out to 100 kpc. Looking for tidal features around massive galaxies, and looking at the growth of intercluster light at intermediate redshifts. And these aren't the only things that you can do in the low surface brightness universe with HSC, but just to give you a little bit of a sampler. Okay, so what do I mean by dwarf galaxy? In this context, I'm purely going to be talking about bright dwarfs. Why study dwarf galaxies? Well, they're important in our overall understanding of the physics that govern the universe. And then why now? Well, wide field surveys offer this avenue towards statistical and structural studies of dwarfs. Okay, so now that we've gotten the definitions out of the way, there's really three main themes that I want to touch on today. What governs the assembly of dwarf stellar structure? How do special classes of dwarfs relate to the overall population? And really, actually, what does the dwarf population look like? Which is phrased a little bit flippantly, but I think captures the point. And if we start with the assembly of dwarf stellar structure, today I'm going to be talking about the origin of dwarf stellar halos. So from left to right, I'm just showing a few examples from theory and resolve star work about predictions for the shape, the age separation, and the overall surface brightness of dwarf stellar halos.
Can I ask here, Erin, these shape predictions, what kind of extents are they thinking about when they say the shape of the stellar halo? Is it kind of like probing the whole dark matter halo, or what do you mean here by shape?
So these shapes in particular are feedback driven, are star formation feedback driven, where they separated. It's a simulation, so they just separated by age, I believe, without an extent cut. But these are largely closer in to the galaxy than you would expect for something like the accreted component.
Okay, great.
I'm so used to these simulations, doing sort of a semi-analytic kind of a kludge. But how do you, I mean, so you would be really super sensitive to how that's done or if it's done.
Mm-hmm.
So can you tell a little bit about what was done here? And how, I mean, whether people are able to robustly simulate that?
Yeah, so that's a really interesting point that I'm going to talk about a little bit more later, if that's okay. Okay, so nearby dwarfs show irregular star formation. This is SMC, so extremely nearby. And they also show a smooth old stellar population. And it's very tempting to make this structural analogy between this irregular star formation and smooth old outskirts as the sort of Milky Way disk and classical stellar halo. But if we think about that a little bit more, we can say, okay, when we think about these dwarf galaxies as hosts, there's plenty of dark matter halos to accrete. This is just the halo mass function. But there's not enough stars to build a classical accreted stellar halo, or at least accreted by minor mergers in the way that we think about for more massive galaxies. So this is star formation efficiency as a function of halo mass. And what we think of as hosts in this context are really these 10 to the 10, 10 to the 11 solar mass halos. So they're already kind of falling down the star formation efficiency slope. So any satellites that they accrete will be lying even further below or at even lower star formation efficiencies. So it's not clear that they could accrete a classical stellar halo that is bright enough for us to observe in wide field imaging. And indeed, if we look at a more detailed simulation of an accretion-only stellar halo, so this is surface brightness versus radius, we can see that even at a few kiloparsecs, the surface brightness of the accreted-only stellar halo, so kind of minor merger-driven stellar halo, is very dim. So 30 to 32 magnitudes per square arc second, which is already something like 4 magnitudes per square arc second, deeper or fainter than what we can observe with HSC. Yeah.
What's the relative stellar mass between, sorry, what fraction of the stellar mass are you talking about when you're talking about this stellar halo?
So for the accreted stellar halo, I think this is about 4% of or their prediction for this particular case is about 4% of the total stellar mass. But when I'm going to be talking about stellar outskirts in general, I'm going to talk about a slightly different information channel.
So, but, well, I mean, just like the two pictures you showed of the SMC in the
Mhm.
previous slide, right? You had the star formation and the ultra halo. What's the relative mass between those?
I'm not sure of the answer for that for the SMC in particular.
But really roughly.
Roughly, I think it's on the order of it's a little hard to say because they do age separation, so that's the entire old component. So
Yeah, that image
it's-
was everything. So
Yeah.
it'll be the disk and all the. So it won't be, it'll be like subtract that disk and then there's some outskirts. And,
Okay.
And I think
Yes.
ballpark people normally say that the accreted stellar halo is like 1 to 10% of the entire stellar mass of a galaxy, but that's different than the image you were showing.
right,
It looked like the entire thing.
right.
But when they do these simulations, for example, you can imagine that when there's a minor merger, it simulates star formation and so on. Is that all in there, or are they just talking about like gravitational trapping?
For oh, it's not up anymore. For the halo shapes paper, that's star formation feedback driven, they do include star formation explicitly. For this one that I'm showing right now, there's no star formation included. Okay. So we think that classical halo formation isn't really possible for these halo masses, but of course, there are some proposed solutions to generate stellar outskirts anyways. So the first is in situ stellar halos from star formation feedback. And this idea is basically that dwarf galaxies live in shallower potential wells. So star formation feedback is able to drive gas to larger radii. And this can drive overall fluctuations in the potential, which causes the outwards expansion of the stellar component as well. So this is an example from the fire simulations. Left-hand panel shows all stars. The right-hand panel shows the young stars only. And in this formation scenario, almost all dwarfs would host this kind of in situ stellar outskirts component because they're all undergoing this star formation feedback cycle. The second is major mergers between dwarfs. So the idea is, okay, if we can't form a classical stellar halo from minor mergers, what about mergers between dwarfs of approximately the same mass? And this idea is essentially predicts that a minority of dwarfs in wide field imaging should have observable stellar halos because a minority of dwarfs have gone through a major merger recently enough for their stellar halos or for the resulting stellar halos to still be observable in wide field imaging like HSC. And of course, dwarf mergers are an observed phenomenon, even at, well, they are an observed phenomenon, but they're fairly rare at low redshifts. And then the last is really more an observational bias question. So most of the galaxies where we've seen these extended stellar outskirts have been with resolved stars, and thus most of them have been within the local volume or within the local group. And so it's not entirely clear that the stellar outskirts that we see in resolved stars and these nearby dwarfs are a generic feature of dwarf stellar structure, because there is, of course, this environmental presence of more massive galaxies like the Milky Way and Andromeda. Okay. So coming back to kind of harping on HSC as this tool for statistical studies of dwarf structure, we can say what we really want to know about is the intrinsic structure of the galaxy. Galaxies are obviously three-dimensional structures, even though we always see them as projected two-dimensional shapes. And HSC is really the first avenue to infer the three-dimensional shapes of these dwarfs as a function of radius at low masses. To give some fast facts about this particular dwarf sample, these are 6,700 dwarfs, redshift less than 0.2. These are all spectroscopically confirmed, either SPSS or gamma. And because of the depth and resolution of HSC, we can non-parametrically measure their ellipticity profiles from 1 to 4 effective radii. And clearly, it's not entirely clear why I'm suddenly talking about ellipticity profiles when I really want to know the three-dimensional structure. So let me back up a second and take this kind of toy case. So say we can characterize a galaxy as an ellipsoid at some given radius with axis ratios C over A and B over A, or principal axes A, B, and C. A is the largest, C is the smallest. this is what we want to know. We want to know this shape. But of course, what we see is this observed projected ellipse with some axis ratio b over a, or little b over a. And our goal is to infer the shape of this ellipsoid from this two-dimensional projected shape. Clearly, as I've set up the problem, it's intractable. We can't go from a single two-dimensional shape to the three-dimensional shape. But what we can do is say that these galaxies are drawn from the same overall shape distribution. So just to be clear, I'm not saying that they all have exactly the same shape, but for this example, I'm going to say that just look at this one ellipsoid, just to be clear. But if we take this one ellipsoid and say that the galaxies are drawn from the same shape distribution, then we can say maybe we'll see this ellipsoid from this projected or from this viewing angle and see a largely kind of high ellipticity or low b over a ellipse. So this will have a projected axis ratio that's quite close to 0. But if we look at this ellipsoid from a different direction, we might end up seeing something that's pretty circular and have a high b over a or ellipticity close to 0. And if we think about viewing this ellipsoid from viewing angles that are drawn uniformly over the unit sphere, then we can think about this characteristic distribution and projected axis ratio that we can use to map back onto the three-dimensional structure of this galaxy population. Okay, now that I've gone through the toy model, let's get a little bit more quantitative with another toy model. So here, this is a figure that I'm going to be showing a lot. This is intrinsic axis ratio b over a and c over a. Down here is disky, so b over a close to unity, small c over a, something like this blue disk. Up in the right-hand corner is more spheroidal, so A is approximately B, which is approximately C, which is a sphere. And then down in the left-hand corner is something that's more prolate or cigar shaped. So B over A and C over A are both small, or B and C are both small relative to A. So if we just think about what distribution of projected axis ratios we would expect for each of these shapes, you can say, okay, the disk, we should see some edge-on views, we should see some face-on views, and we should see a transition in between. And indeed, if we look at the distribution of projected axis ratios, here the blue are the mock observations, and the unfilled black histogram is our posterior sample, or our best fit model in projected axis ratio space. You can see that checks out, that comes to fruition. If we think about a spheroid, we can say, okay, should appear largely circular from all angles. So the projected axis ratio should be close to unity for almost all instances. We see that's true. The projected axis ratio b over a is almost 1 with a sharp peak. And then finally, if we think about this prolate kind of cigar-shaped galaxy, there should be a few views where you're really looking down the barrel, but overall you're going to see a mostly elongated projected shape. And indeed, we see that the projected axis ratio distribution peaks at low b over a and then has kind of the tail off towards unity. And if we turn back to this initial panel again, here the black circles are the input ground truth for each of these toy models, and the filled histograms or the filled contours are our best fit model for each of these toy cases. Okay, so now that we've gotten our second layer of toy model out of the way, let's apply it to some actual data. And this is a rather busy plot, so let me just tell you the punchline first.
Just backing up, the
Yes.
thing you're fitting, I think you can leave in this, okay, but the thing you're fitting is this two-dimensional distribution.
So the thing that I'm fitting is the distribution of projected axis.
Sorry, the model parameters
Yes.
are like
The
some.
model parameters, so we assume that the intrinsic shape distribution is a bivariate Gaussian, so we're fitting the mean b over a, standard deviation of b over a, mean c over a, and standard deviation of c over a.
But just one Gaussian?
Yes, so we're assuming a unimodal population, and we did look at assuming a more complicated distribution, but essentially it doesn't improve the fit
Because
enough
you can
to-
imagine, like, you have a set of disk galaxies, and then you would have another Gaussian that floats around.
Yeah, so we did think about that in the context of the fire simulations, which I'll come back to in a little bit. but we essentially find that this isn't sensitive to a minority population of very differently shaped galaxies up to about 10 to 20%. Okay. Right, so the punchline of this plot is that stellar halos are common in bright dwarfs, and the dominant dwarf configuration is a thick disk and a round stellar halo. So to explain how this figure shows that, in each of these inset panels, now I'm showing the projected axis ratio distribution. So the filled green histogram are the observations. This is what we're fitting. And the unfilled orange histogram is the best fit model in projected axis ratio space. The main panel is this familiar B over A versus C over A. And the orange contour is now the best fit model, but intrinsic axis ratio space. And the unfilled dotted contours or the unfilled dash contours are just the toy models that I showed earlier to kind of contextualize where these galaxies are living. So you can see that at one effective radius, these galaxies are characterized by largely thick disks. So they're not as thin as the extreme toy model that we looked at earlier, but they're largely oblate and have small C over A's compared to their B over A. So they're largely distant. As we go to larger radii, so up to 2, 3, and 4 effective radii, we can see that the galaxies are becoming systematically rounder, moving up towards this more spheroidal extreme. So they're systematically rounder at 4 effective radii, though they're still flattened. They're not perfect spheres. And this is consistent with the in situ picture of dwarf stellar halo formation that I mentioned earlier, wherein all or almost all of these dwarfs should be hosting a round stellar outskirts because the star formation feedback cycle is happening in all of them.
Are the inner and outer axis ratios aligned?
Aligned.
That would also be consistent with the in situ picture, right?
Mhm. So aligned in the sense of is there an isophotal twist, or aligned in the sense of is there a centroid shift?
Twist.
Twist.
Could you just explain what an isophotal?
Sorry. So isophotal twist is essentially when you have say that the isophote looks like this at one effective radius, and then as you go out, the galaxy twists. So we don't see a significant systematic shift in the position angles as a function of radius. If we do the same exercise, keeping the position angles constant, we see the same effect. Okay,
So just to go into physical units,
yeah.
how big should I mean, are they have a fairly common size for a given mass?
Yeah, so the effective radius of these is we span about 10 to the 7 solar masses to about 10 to the 9. At the 10 to the 9, the effective radius typically is 1 to a few kiloparsecs. Obviously going down as you go down in solar mass. Okay. So now we have these observations of stellar outskirt formation around these dwarf galaxies at hand. And the next question is, what does that actually tell us about this overall picture or this overall analogy that I constructed earlier? And to do this, as I kind of mentioned before, we turn to the fire isolated dwarf sample. So just to give a little bit of background about the fire galaxies, these are a cosmological zoom suite. I'm looking specifically at the isolated dwarf runs with halo masses of around 10 to the 11 solar masses. And these galaxies have a baryonic mass resolution of a few thousand solar masses. So this is really the resolution that you need to start thinking about the structure, especially in the outskirts, but about the structure of these dwarf galaxies. And to give you an idea of what these dwarf galaxies look like, especially compared to HSC, here I'm showing mock HSC I-band maps of 4 of the M11, so 10 to the 11 halo mass fire galaxies. And the line contour in each of these shows the isophote at the nominal HSC surface brightness limit. Okay, so for these fire galaxies, there's really 3 questions that we want to answer. 1, do fire dwarfs look like real dwarfs? And actually the next 2 won't make sense until I answer the first one. So do the fire two dwarfs look like real dwarfs? The answer is some of them do, but a lot of them do not. You'll immediately notice that I kind of preemptively sorted the fire two dwarfs into this disky and non-disky category, which I'll explain in a moment. But before I do that, I just want to make the technical caveat that in the simulations, in order to derive stable shapes or stable three-dimensional shapes, we need to use cumulative shapes as opposed to differential shapes that we used in the observations. So here we're separating into young stars versus old stars. But to show that that we're probing the same physical structures, in the bottom left, I'm showing a light-weighted age map, again, weighted by HSC band, and I'll show the populations that we're probing for the young stars and the old stars as a function of radius down on the left.
So at the risk of suggesting something much more complicated, the other thing you could do is look at these dwarfs from a bunch of different directions and ask, what does your procedure say?
Yeah, so we do this in a kind of verification step, but the reason why we didn't do it initially is because of the low number of initial conditions for the fire galaxies.
Yeah.
So you're not really probing, I mean, the limitation of the observational approach is, of course, you only get information at the population level. Whereas the fire dwarfs, there are so few initial conditions that you're really not probing the dwarf population, or you're sampling very discreetly from the dwarf population, which
Right.
isn't necessarily the same as observing the dwarf population in a continuous way of future observations.
So
Yeah.
how many dwarfs are there in are you using the five fire galaxies?
So there's more fire initial conditions now. There's about 12 independent initial conditions, and we also probe different implementations of the fire physics. So these give slightly different results, or I should say that these don't strongly affect the intrinsic shapes. They do give slightly different results in other quantities like the star formation history, but they're not independent initial conditions. So that's what accounts for the overall number of points on this plot, which
But I
is,
guess it seems like they're not enough. Or also, I didn't understand it. You probably said, and it's just brain wasn't caught up. How do you define non-disky and disky?
oh yeah, I was about to get into that. So the disky, so in each of these panels, I'm showing young stars in green and old stars in the orange squares. The unfilled ellipses in blue and red are the observations that I just talked about at 1 and 4 effective radii. And essentially the disky galaxies are characterized by a thick disk without that much triaxiality, so close to oblate, which is B over A equals B over A of unity. So a thick disk in their young stars and a shift towards more spheroidal shapes in their old stars without, while maintaining B over A that's roughly
What I'm
constant.
confused about is the labeling the large overall system or right, the fire simulations have a sort of central pretty big galaxy.
Oh,
don't they?
okay, let me back up. So those fire simulations are
Oh, you're talking about a different set.
different set of
Okay,
simulations.
which is just for finding dwarfs.
Yeah, so the central galaxy are these dwarfs.
Okay, thank you,
Yeah.
sorry. And so
Okay.
then you, by your previous study,
Mhm.
you categorize them as disky or not disky.
Right, so these are those that host a thick disk. And then you can see that there's also a very large complement of fire galaxies at redshift 0 that do not form a thick disk or any sort of disk in their young stars yet, and kind of also don't show a systematic change in morphology in their old stars.
Based on your previous technique. I'm a little confused because you were using the C over A and B over A to infer information.
So in the simulations, we can measure the
Right,
intrinsic shapes
right,
outright. We can, yeah, just go in and measure the 3D shapes for each individual galaxy.
So if you hadn't made a decision of how to categorize them, they would have all been in just one plot.
Yeah. Mhm. So the separation in 2 plots is purely a narrative choice that I'll explain in a moment. Sorry, I think I had a question.
So these are central galaxies and field halos.
Yes.
Did you do any sort of, is there, in the HSC sample, did you do any sort of environmental
Yes.
separation? to-
So in the HSC sample, we both looked at color separation and environmental separation. Essentially, what you see in both cases are that the satellite galaxies and independently the red galaxies tend to be less disky at low radii, at small radii, compared to the central and or blue galaxies, which is not surprising given the overall bimodality or the overall color morphology bimodality which you see at higher masses, but they both host these rounder stellar outskirts. This is just with the isolated fire dwarfs, but you could think about doing this with the satellites of the more massive galaxies as well, but it's not included in this work. Okay, so the young stars in green, old stars in orange. And really we can think about two distinct morphological classes, which I'll come back to in a second. These disky dwarfs that have a young disk and an old stellar spheroid, and then these non-disky dwarfs that don't host a young disk and have a variety of shapes in their old stars.
Really, it seems like they're all going to the same place. The orange squares all seem to be going to the center of the plot, regardless of where the green dot
Not in the
is.
left, aren't they just going up on the left?
Oh, yeah, so just thinking about the right-hand panel. I think that is true, and I'll come back to that in a moment. But a variety of shapes in that they are not monotonically moving up in C over A. I should
Okay.
rephrase that. Okay. So now that we've talked about whether fire dwarfs look like real dwarfs, we can really go to these next two questions, which is first, where do the
Oh,
stars?
wait, sorry, before. What was the thing in terms of either the input physics or the initial conditions which separated out those two sets of galaxies?
Oh, I will talk about that in a second.
Okay.
So where do the stars and simulated stellar outskirts originate? And then what differentiates the dwarfs that succeed in forming a disk from those that don't? Which is your question, I believe.
Yeah.
Okay. Okay. So when present, both disks and halos are in situ structures in the fire simulation. So here I'm showing stellar mass versus a proxy for the accreted fraction. The filled points are star particles with ages greater than 12 gigayears. And then the unfilled circles are just all of the star particles with a radius greater than 10% that of the virial radius at redshift 0. And you can see that as a function of stellar mass, where the galaxies monotonically increase in their accreted fractions and their halos as a function of stellar mass. So the more massive Milky Way-like galaxies are dominated by this ex situ fraction, which is completely expected given the connection with classical stellar halos. Whereas as you go down towards lower dwarf masses, the in situ component becomes more and more significant. So both the observable dwarf stellar halos and the direct fire 2 results support this in situ origin for dwarf stellar halos or dwarf stellar outskirts. Okay, then finally, what differentiates dwarfs that succeed in forming the disk? So these non-disky dwarfs are gas depleted first. So here I'm showing stellar mass versus H1 mass. The gray points are an observational sample. The green points or the green crosses are non-disky dwarfs. Purple crosses are disky dwarfs. Gray crosses are non-dwarfs, so you can just ignore that. But you can see that the non-disky dwarfs tend to be gas depleted, both relative to the disky dwarfs and relative to the observational sample. And the disky dwarfs tend to lie pretty well on this H1 stellar mass locus that's defined by the observational sample. And the non-disky dwarfs also seem to have a more recent recently bursty star formation history as compared to the dwarfs that succeed in forming a redshift 0 disk. So here I'm showing stellar mass versus recent star formation burstiness in the last 2 gig years. Colors remain the same, and the non-disky dwarfs tend to be burstier at more recent times compared to their disky, more quiescent counterparts.
Sorry, I'm having trouble mentally keeping up, I guess. Repeat which are the observations and which are your simulations.
Yes, so gray points, the small gray points are the observations. All of the crosses are simulations.
Okay. And over on the right,
Over on the right, everything is simulations. Oh, yeah.
Just so I understand better, there's some overlap in green and blue crosses on the left.
Mhm.
When you characterize some as green and some as blue, are you saying that at any given stellar mass, there's a lower gas content?
So
compared to the blue? Or-
here, the colors do not map onto the gas fractions. These are the same morphological classifications that I mentioned before. So either succeeds or does not succeed in forming a disk at redshift 0, a young stellar disk. So the color is independent of the color assignment is independent of the H1 content. It's just that the non-disky dwarfs also tend to have less H1 for their stellar mass.
This is kind of, so, but those higher mass ones,
Mhm.
I can't tell if they're blue or green.
Yeah,
Oh, they're
I actually have the same
non-dwarfs,
problem.
non-dwarfs.
Ah,
There
right.
we go. Okay.
but so I'm sorry, is the message, the message of blue, non-disky dwarfs are gas depleted and burst state,
Mhm.
that's a simulation prediction,
Yes.
nothing to do at the moment with the HFC.
Yeah, so one thing that I think would be really interesting to do is to ask, so the non-disky dwarfs, for example, are below the H1 locus, but they're not living out in unphysical space. There are observations that cover that. So I think one interesting thing to do is ask whether the shapes of particularly these observed galaxies that appear to be a little bit gas depleted have more similar shapes to the non-disky dwarfs in fire. The technical barrier is just that to do this inference, you need a large sample of dwarfs because you need to sample this, you need to sample this array of projected shapes in order to infer the intrinsic shape. So there's just not enough, the sample isn't quite large enough yet to do that inference.
I guess in the left plot, if you just looked at the crosses,
Mhm.
they don't very well represent the data.
Yes, they don't.
Is that
Not well.
because they tried to simulate certain kinds of galaxies and therefore don't expect it to be representative of the data, or was what they were simulating supposed to be representative of the data?
Nominally, what they're simulating should be representative of the data.
What is this y-axis? I don't get this.
So this is just the amount or the stellar mass formed in a burst over the total stellar mass formed in the last 2 big years.
Okay.
Yeah, I just replaced it with a more qualitative title for to make it visually clear.
So just to sort of imprint, if it's non-disky, according to the observations, it should have more gas than the simulations are giving.
If it's not disky, according to simulations, it should have less gas.
Than as observed.
All the observed dwarfs are disky. There's no population of non-disky isolated dwarfs.
We're getting so.
Yeah. I mean, it's very interesting, but like this results a lot, that previous plot is very interesting because there's a huge population of, it immediately means they're doing something wrong with the dwarfs.
Right. So
There's
I
something
think,
wrong with the simulations.
yes, and I think that the fact that they're so bursty at low redshift is probably connected to their gas depletion, that their feedback is really, 1, preventing the formation of a disk, and 2, depleting their overall gas fraction, at least in H1.
But it's not like recent merger activity.
No, it's not. Okay, so what differentiates dwarfs that succeed in forming a disk? Disky dwarfs, oh, sorry, this is a typo. Disky dwarfs are less bursty and not gas depleted.
Yeah, I have a,
Yeah, there are too many negative.
Okay,
But
disky
anyway,
dwarfs
I'll ask
are
for-
more quiescent and they have a lot of H.
they're less
Let's-
bursty and less gas depleted.
Yes.
Less modifies both of
Oh,
those. I think, yes.
wow. Afterwards, you'll make a little list of them.
Yeah. Okay. I'm very much going over time, so I'm actually gonna skip the second part. Just jump forward. Okay, so if you're interested, I'd love to chat about how special classes of dwarfs relate to the overpopulation, but just to finish up, actually, what does the dwarf population look like? And to answer this, I'm part of the Marion survey, which is a mass complete view of the dwarf population. And to give you some more survey fast facts, the Marion survey is a medium band filter survey that's set to cover 860 square degrees with D count. And the main idea is that we've got one medium band filter on O3 and H beta, and the other medium band filter on H alpha. So the idea is to pick out star-forming galaxies at redshift 0.05 to 0.1, and specifically targeting a mass complete sample of star-forming dwarfs down to about 10 to the 8 solar masses in stellar mass over this redshift range. And here's my second collaborator slides. This is led by Alexi Lotoa at Santa Cruz and Jenny Green at Princeton, and a lot of other great collaborators. And the Marion sample, when complete, should have more than 100,000 dwarfs. And as I said, mass complete to 10 to the 8 solar masses in stellar mass for star-forming dwarfs. To give you a more visual idea of what that means, here I'm showing mass size. The blue points are detections or expected detections in the Marion survey. The red points are the same equivalent scaling for the gamma survey. So scaled to the volume that is probed by the gamma survey in this redshift range. So just try to compare apples to apples. And then the gray are non-detections in our medium band, so either not star forming vigorously enough or outside of the surface brightness limits that we expect. But in any case, you can see that the Marion survey should both increase the overall sample of dwarfs by 2 orders of magnitude over what's been done spectroscopically before, and also go to significantly lower stellar masses while remaining mass complete in these star-forming galaxies. And there's 3 main pillars or 3 main science pillars that we have to execute with the survey. The first, as I mentioned before, is to get the census of star-forming dwarfs in this target mass at redshift range. The second is to probe the stellar to halo mass relation using weak lensing on these dwarfs, which is the main science driver of why we need so many modern B3 mass complete. And then finally, this studies of dwarf star formation and structure, including things like mass size, but going also into things like H alpha luminosity functions and really H alpha morphologies that we can get because we have this medium band. Okay, and to summarize, so dwarf galaxies are key tools to probe star formation and dark matter, and they're only now becoming widely available at significant distances. Dwarfs in HSC show a generic thick disk and round halo structure consistent with in situ origins. Fire 2 dwarfs that host disks also host round and in situ stellar halos, and Fire 2 dwarfs that do not host disks tend to be bursty and gas depleted. I didn't get to this, but preliminarily, UG ultra diffuse galaxy star formation inefficiency can be explained by their diffuse stellar structure. And then finally, stay tuned for the first mass complete sample of star forming dwarfs out to redshift 0.1. Thank you.
The Marion survey, currently there's no good way to get H1 masses for that many galaxies that faint. Is that right?
Currently, yes, but I think Wallaby will do very well. So at 0.05, redshift 0.05, Wallaby should be H1 mass complete down to about 3 times 10 to the 8 solar masses, and then at 0.1, about 10 to the 9 solar masses. So
Okay, so you're
not quite as
so you won't see all 100,000, but you'll see a lot of them.
right. Yeah,
Okay.
I missed where you're getting the spectra for the Marion survey.
the spectra. Sorry.
So it's only photometric.
So right. So there's 2 medium bands on O3 and H alpha, and then these are all also over HSC fields. So the broadbands, so it's essentially going to be semi-photometric redshift, but using the power of 2 medium bands to really get at the.
Right, so that's how you're getting
Specific
H alpha,
sets.
it's just from this one band around.
Oh, yes, yes.
But then you also know, like, they'll just sort of, if the dwarf galaxy's at that redshift, in your redshift band, they'll just light up, and you
Right.
won't know whether you probably won't know whether they're 0.05 or 0.1.
Yeah, so from our predictions, part of the reason why we have the two median bands instead of just H alpha is to try to get some dynamic range in constraining the redshift within 0.05 to 0.1,
Right,
because we can do pretty well just getting dwarfs in that bin if we
Right.
just have H alpha, but to really try to get at the redshift some precision within that bin, we need the second median band.
okay, so you can get some precision in
Mhm.
there, yeah.
Of course, not as good as spectroscopic follow-up, but
Oh, yeah.
it'll place you somewhere in the bin.
I just am sure that I leave with the right message. So the second line, I understand, and that's what Mike was reiterating. And the next one about the fire two, would it be fair to say that roughly half the fire two dwarfs
Oh, that's a good,
actually are wrong?
yeah,
Or
so
is
that's
it
a
just-
good question that I think you mentioned earlier that I didn't come back to. So about whether there could be a secondary population that we just don't pick up in the observations because we're enforcing this unimodal model. So approximately 60% of the fire dwarfs are non-disky at redshift 0. And we would expect to see a significant change in our observational results if that population was greater than about 10 to 20%.
But back to the input physics in the fire too, right? There was no clear separation of something they changed in all the knobs and buttons they've got to be disky or non-disky in the final result, right?
Right, so we also tested a array of their different physics implementations, and we didn't see a huge change in whether the galaxies ended up disky or non-disky at redshift 0. So I would agree with saying that it's unclear exactly which knob you need to change in fire to change this balance between dwarfs that succeed in hosting a disky at redshift 0 and those that don't.
Still drawn back to like merger activity seems like it would explain this, right? It disrupts the disk and it gets rid of a lot of the gas.
Mhm.
So, but like if you just looked at time since last major merger for those two classes, was there any difference in that distribution?
So I didn't look at that specifically, but one, I think, relevant thing to note in observations with which Sarah has thought about some, is that when you have dwarf mergers, you're not necessarily depleting a lot of gas. More gets moved to larger radii, but it doesn't completely leave the system. So the mechanics are a little bit different than when you're thinking about mergers between more massive galaxies.
Right, although that is an observational statement. The
It's true.
simulations that might be the thing the simulations aren't getting right.
That is true. Yeah,
And things like the rate of mergers, like the
Right.
rate of mergers is really small, like in reality.
Yes, got it.
But like you can't explain 60%, unless,
Well, not in the data, but
Yeah.
They
But
might
in
have
the
picked weird, they might have
simulations.
picked weird initial conditions.
yeah.
yeah, that is something to think about for the fire simulation. Yeah.
But even in simulations, that gas shouldn't get unbound, right? It should still be there. Theoretically. In mergers of dwarfs.
I guess so. I don't know.
I mean, that, because part of my reason for saying that is both observational and theoretical, not from fire, but from modeling dwarf interactions. It does seem like the gas gets put out to large distances and hangs out there for a while, depending on exactly your interaction, but it shouldn't necessarily unbind the gas. You don't really lose it unless you have a lot of starbursting stuff happening, or if you're accreted to something larger eventually.
Do you have the information to like look at those? I mean, this is probably going too far down, but look at those galaxies at different epochs. Like, do they change? Like, do they have a disk and then it goes away and then it comes back and then it goes away?
Yeah, so in the fire galaxies, it doesn't seem like the non-disky dwarfs ever hosted a disk. But that's not something that I looked at in particular depth for this paper.
They never hosted a disk.
So it doesn't seem like they settled into a disk and then were later destroyed, and that's just the snapshot we ended up with at redshift 0.
But they are forming stars, just not in a disk.
More or less, Yeah, they're all forming stars. The disky ones tend to be less bursty.
What about the dark matter distribution? In the fire simulations, is it cuspy in the center? Is it very
Yeah.
broad? Where are these baryons and stars relative to the dark matter?
Yeah, so one of the reasons why this bursty star formation model is preferred is because it helps form cores in these fire cores.
And are the cores well established in dwarfs of this mass?
I
mean,
believe
observation.
that they are, but I didn't look at that specifically.
That's
you s-
actually Justin Reed, who's gonna give a
Oh,
seminar here. That's really his work in H1 showing core dwarfs. I'll try to find that reference for you.
So they're solving one problem and creating another one.
Yeah.
Okay, excellent. Keep everybody employed.
Cool.
Thank you.
Thank you. You didn't really ask if there are any questions from online.
Oh, somebody does have their hand up.
Yes, you have a question?
We can hear you. Oh, now we can't hear you.
Can you hear me now?
Yes.
Okay. I have a question about the dark matter. You mentioned that dwarf galaxies are useful for investigating dark matter. I wonder if there have been any attempts to look at alternatives to dark matter. For instance, looking at binary interactions between pairs of stars, or looking at some of the new versions of MOND that seem to agree with the background infrared.
Yeah, so just to make sure I understood the question is, how much have dwarfs been used to constrain alternate models to dark matter?
Yes.
Okay. So for the binary star interactions you talked about, that's much closer than what I think about. I'm more in the regime where we measure distances in redshifts instead of megaparsecs. But for the broader question, I think that they are useful. One of the things that I'm most interested in is essentially understanding the baryonic processes, because kind of relevant to talking about this core cusp formation. I think we really need to understand the baryonic processes in order to say something constraining about dark matter using these systems, because all of the star formation physics and these larger scale environmental processes affect their structure so much that we kind of need to understand the baryonic physics in order to use these as a probe for alternate models of dark matter.
A related question about dark matter. Whatever it is that we learn about dark matter from those observations, how well does it mesh with observations of gravitational lensing that would result from the dark matter?
Yeah, so when I talked about measuring the stellar to halo mass relation, that's one of the main science pillars of the survey, but we're still in data collection, so we haven't made that measurement yet.
Thank you.
All right. Thanks. I'm gonna. Let me just move by here.
I'm trying to find the paper. I couldn't find it right now.
Erin? Stop. We're introduced. I'm glad that's right. Nice to meet you.